In this segment, we're going to talk about how to do inference in hidden Markov models using the Viterbi algorithm. So HMMs are a model of this joint distribution over P of y and x, given by the following formula that reflects this kind of Markov assumption over the y's and this emission distribution where each x is emitted from a corresponding y. But the thing that we really want to compute for inference, especially from the perspective of a task like part-of-speech tagging, is the argmax over y of P of y given x. That is to say, given a sentence, what is the most likely part-of-speech tag sequence that could have produced that sentence? So this is a little bit tricky because our model is kind of set up in the other direction in some sense. Like it kind of generates a sequence of y's and then generates x's conditioned on those y's. How do we flip it around to actually figure out what the most likely y's are given the x's? So we can do this by a little bit of rewriting and rearrangement. So this is equal to the following. And so what we've done here is we've multiplied the top and bottom by P of x, and when you multiply the top by P of x, it kind of combines via the chain rule to give you this joint distribution. And now the bottom is this P of x term. And this term is constant with respect to y. So from the perspective of argmaxing over y, we don't actually need to worry about it. So we can say that, all right, the kind of numeric value of the max we get from this won't be the same as P of y given x, but it'll give the same maximal sequence y. And then we're going to apply our other favorite trick here when dealing with maxes, which is that we want to max the log probability of this. All right, so now that we've rearranged this, we've got something that feels a little bit more tractable. And now we're going to expand this out. And I'm going to write these as y twiddle here. And so on and so forth. So we have this fairly complicated expression, and we can't max over it directly, obviously, because this would require an exponential search over all the different possible values of the y twiddle i's. And so what we're going to do in order to do this max is appeal to dynamic programming. And so I'm going to tell you basically what the dynamic program looks like, and then we're going to see how that kind of falls out of the structure of this computation, and in particular, how it takes advantage of this Markov property of hidden Markov models. Okay, so we're going to define our dynamic programming matrix here. And this is an n by t matrix where n is the sentence length and t is the number of tags in our tag set. And the semantics of this is going to be the score of the best path ending in y twiddle at time I. So kind of starting from position 1 at the beginning of the sentence, we're going to compute a partial max, but that max is going to be anchored to this particular tag y twiddle at this time step. And so, it's going to represent some amount of kind of maxing and having done inference, but it's also going to maintain uncertainty in the sense that at a given time step, we are tracking the best max for each possible tag that we could be in at that time step. All right, so let's define our dynamic program here. So v1 of y twiddle is log p of x1 given y twiddle plus log p of y twiddle. And this is basically, when you tell me, okay, I have to be in this particular state at the first time step, this is the score that is associated with that. And you can think about this as kind of all of the terms that kind of come up to that point in the computation of the joint probability. So kind of graphically, again, we're kind of thinking about, okay, what are all the scores up until this point? Well, there's two nodes that we need to generate here. We need to generate this one, and we need to generate this one. And then it is true that this next node over here depends on the value of y1, but that's going to fall out in the recursive case. And so here's what that case looks like. So we have the emission at the current time step. And then we have max over the previous time step. So what we're doing here is we're saying, okay, in order to compute we've computed basically the scores for, let's say, the first time step here. And then in order to compute the scores for the second time step, what terms do we need to account for? Well, we need to account for this emission here, which corresponds to this term. And we also need to account for the transition. Now, the transition depends on the value of the previous tag here. And remember that at the end of the day, our goal is to compute the kind of best sequence ending in this tag at this particular time step. And so what we do is we think about, okay, what are all the possible previous tags that could have brought me here? And so that's what this max over y twiddle prev is doing. We are considering all of these different possibilities and saying, okay, for each one, we already know the best path that gets you there, and then we can compute the transition probability and then add the new emission. And then that's going to give you the best tag or the score of y twiddle for the best path getting you there at this time step, and you can kind of proceed from there. All right, so just to motivate a little bit why this works, recall that what we were doing was maximizing y twiddle n through y twiddle 1. I'm going to write it in this direction. Etc. If you just look at this sequence of terms, which I'm not going to write out, it turns out what you can do is you can move the max over y twiddle 1 basically all the way over here to the beginning. And you just end up with those first couple terms involving this, that are involving y1 here. And so it kind of very naturally emerges from just looking at what happens when you apply these maxes to this sequence. You can kind of commute the maxes past all the terms that don't involve them. And then if you kind of deal with the sequence in this like right to left fashion and say, okay, I'm going to first figure out what's going on with this y1 term and then kind of push it forward from there. And the only thing that makes it tricky are these transitions. Now, notice again that the reason that dynamic programming was necessary to begin with was because we had these transitions involved, right? If we didn't have transition probabilities, if it were just emissions, we would be able to just independently max at each time step, but the transitions sort of end up coupling everything together. But because of this Markov property where we only depend on the one previous time step, we can get away with this relatively small dynamic programming chart that just maintains basically a score for the kind of tag at the current time step. All right, so let's just make this algorithm a little bit more explicit. Okay, so this computation of VI of y twiddle is just going to use the formulas up above. And then at the end, and you basically have to push things forward and account for the stop symbol. And then this equals the max over y log p of x comma y. And so that's the result that we want. Although, hey, wait a minute. What we're doing right now is we're computing a max. And what we wanted was the argmax. We wanted to know the actual path rather than just like the numeric value of this log probability. And so there's an extra step here that I'm not going to show where you have to track what are called back pointers. Essentially, at each step, when you compute the VI of y twiddle during the recurrence, there's some y prev that this came from, and you want to keep track of what that is. Because then at the end of the day, you want to say, all right, here's the final score I got. What was the kind of previous tag that along this path that got me here? And then you kind of unwind it and you can go back and actually reconstruct the sequence of tags that got you here in addition to just the score. Okay. I'm going to very briefly show an example of what this looks like. So we're going to follow the same rough template for this that we've been using for a couple of examples so far. And what I'm showing here are log probabilities. So these are not exactly going to sum to 1, but the Viterbi algorithm, although we're defining it in terms of probabilities, you could actually deal with any kind of real valued scores here. We're going to see that when we come to conditional random fields. And in fact, the Eisenstein book kind of defines it in that terminology as well. So we have our favorite they can fish example. All right, and so what we do is we define our chart V. I'm going to write VI of y twiddle here. It's a little bit overloaded with the verb tag. And we're going to do the following sentence. They can fish, meaning they can put fish in cans, right? And then we're going to have this extra kind of column, I guess, for the stop symbol. And we're gonna think about basically transitioning to a kind of a special state there. So we're not going to go through all of this. It's a good exercise if you want to check your understanding. I'm just going to fill in the first two values here. So for the first cell, we have the initial probability of noun, which is -1, and then the emission probability of they given noun, which is also -1, giving you a -2. And then we have the same thing for verb, which is -4, taking, again, this value here, and then also this -3 over here. All right, so then what the recurrence looks like is for this cell, what we need to do is say, all right, we have to think about what are the two possible places we could have come from here. And we could have come from this cell. And so what we would get there is the transition from noun to noun, which is an additional -2. And then we would also get the emission of can given noun, which is a -3. So we have a -2 from the value of the previous cell. We have a -2 from the transition. And we have a -3 from the emission. And that gives us a -7 here. All right, and we have to think about another possibility here as well, which is the following, which is what if we came from the -4 cell here? So in this case, we would have -4 from the prev. We would have the transition from verb to noun, which is a -1. And then we have the emission, which again is -3. So that's actually the same between both of these. And in this case, we get -8. Okay, so when we're applying this max then, we kind of discard this possibility, and -7 is what gets chosen. And so the most likely way to get to this second can being a noun is to have they also be a noun. Okay, and I'm not going to go through the whole computation, but it turns out that the best way to get to this cell is have they be a noun and then can be a verb. And this kind of makes sense given our intuition about the sentence. So we end up with -2, the transition from noun to verb, which is -1, and then the emission of can given verb, which is -1, and that's a -4. All right, so you could push the rest of this computation forward. Notice that we do need to keep both of these possibilities alive, even though this lower path, having can be a verb, looks a lot better. And the reason is because there could be some other word coming up that makes us reevaluate how we analyzed the sentence so far and say, okay, actually, it really does seem like that can was a noun. You don't want to kind of commit yourself greedily to doing the wrong thing when there might be more information that tells you something further down the road. Okay, so that sort of tells us how the Viterbi algorithm works. The last thing I'm going to mention about it from the perspective of implementation and debugging is that a very good way to check this is to try it explicitly on a small example. So it's exponential to enumerate all the possible sequences, but computers are pretty fast these days, and when you have just 4 or 5 words in a sentence, you actually can just enumerate them with a bunch of nested for loops. And so you should be able to confirm that this dynamic program and this algorithm is giving you the same result as explicitly doing this max over all these possible sequences. So this is how we're going to do inference in hidden Markov models, and it's going to set the stage also for inference in conditional random fields. So generally, this is a very useful tool for dealing with these kind of sequence models where you have pairwise dependence between adjacent decisions. And that's the end of this segment.